Imagine you're in the most powerful spaceship ever built. You've got engines that can accelerate forever, unlimited fuel, and all the time in the world. You point your ship toward a distant star and push the throttle to maximum. You accelerate. Faster, faster. You're approaching the speed of light. And then something impossible happens. The harder you push, the less you accelerate. It's as if the universe itself is pushing back against you, refusing to let you cross that final threshold. Here's the shocking truth that will change how you see reality forever. You can't reach the speed of light. Not because we lack the technology, not because we haven't figured out the engineering, but because of something far more profound and disturbing. The laws of physics themselves conspire against you. And here's what will absolutely blow your mind. The faster you go, the heavier you become. Your mass increases without limit as you approach light speed. To actually reach it, you would need to become infinitely massive. You would need infinite energy. The entire universe doesn't contain enough energy to accelerate you, a human being with mass, to the speed of light. But wait, it gets weirder, much weirder. Because light itself doesn't experience time. From a photon's perspective, the moment it's created and the moment it's absorbed happen simultaneously. The entire history of the universe, all 13.8 billion years, passes in literally zero time for light. Think about that. Light travels at the speed of light, obviously, but it doesn't experience the journey. And you? If you could somehow reach that speed, which you can't, you would essentially cease to exist in any meaningful way in the flow of time. Before we dive deep into this rabbit hole, do me a huge favor. If you're ready to have your understanding of reality completely transformed, hit that like button right now. And subscribe, because this is going to be a journey unlike anything you've experienced before. Also, drop a comment telling me where you're watching from and what time it is for you right now. I'm genuinely curious. Are you watching this at midnight in Tokyo? During lunch break in New York? Morning coffee in London? Let me know. Because here's the thing. Time itself works differently than you think. And by the end of this video, you'll understand why your now isn't the same as someone else's now on the other side of the world. Let's start with something that seems incredibly simple. Speed. You think you know what speed is, right? It's how fast something moves, distance divided by time. If you drive 60 miles in 1 hour, you're going 60 miles per hour. Elementary school math. But here's the first crack in your understanding of reality. What if I told you that speed isn't really about movement through space at all? What if speed is actually about movement through space-time, and you're always right now sitting still in your chair, moving at exactly the speed of light through space-time? Your mind should be doing a backflip right now. How can you be moving at the speed of light while sitting still? Here's the revelation. You're not moving through space, so all your motion is through time. Think of it like this. Imagine you have a car that can only go 60 miles per hour total. You can go 60 miles per hour north, or 60 miles per hour east, or 30 miles per hour north, and 30 miles per hour east. Using Pythagorean theorem, roughly 42 miles per hour in each direction. But no matter what, your total speed is always 60 miles per hour. You can redistribute how that speed is divided between directions, but the total never changes. Space-time works exactly like this, except instead of north and east, you have space and time. And your total speed through space-time is always the speed of light, which we call c, approximately 186,282 miles per second, or 299,792,458 meters per second. When you're sitting still, all of your motion is through time. You're moving through time at maximum speed 1 second per second. But the moment you start moving through space, some of that motion through time gets converted into motion through space. The faster you move through space, the slower you move through time. This isn't philosophy. This is measurable, testable physics. In 1971, physicists Joseph Haffel and Richard Keating conducted an experiment that proved this beyond doubt. They put atomic clocks on commercial airliners and flew them around the world. When they compared these clocks to identical atomic clocks that stayed on the ground, the flying clocks had measured less time. The difference was tiny, only a few hundred nanoseconds, but it was exactly what Einstein's theory of relativity predicted. The clocks that moved through space on the airplanes moved more slowly through time. Think of it like a speed budget. You have exactly 299,792,458 meters per second to spend on motion through spacetime. Right now, you're spending all of it on motion through time, so you experience 1 second per second. But if you were on a spaceship moving at 50% the speed of light, you'd be spending half your speed budget on motion through space, which means less is available for motion through time. Time would slow down for you compared to someone standing still. Now here's where it gets really interesting. Light photons spend their entire speed budget on motion through space. They move through space at exactly c, which means they have nothing left for motion through time. From the perspective of a photon, time doesn't pass at all. The photon exists in an eternal now, where its creation and destruction are the same event. And this is why you can never reach the speed of light. Because to do so, you would need to spend your entire speed budget on motion through space, leaving nothing for motion through time. You would need to stop moving through time entirely. You would exist in a frozen eternal moment, experiencing all of your journey instantaneously. But here's the catch. To reach that state, you need energy. Lots of it, and the closer you get to light speed, the more energy you need. And here's the real kicker. You need infinite energy to make that final jump. Let's put some numbers on this to make it concrete. Say you're in a spaceship with a mass of 1,000 kilograms, about the weight of a small car. To accelerate you to 90% the speed of light, you'd need about 1.29 times your rest mass energy, or about 1.16 times YY joules. That's the energy of about 28 megatons of TNT, roughly the yield of the most powerful hydrogen bomb ever tested by the United States. But to get you to 99% the speed of light, now you need 7.09 times your rest mass energy. To reach 99.9%, you need 22.4 times your rest mass energy. See the pattern? The energy requirement doesn't grow linearly, it grows exponentially. And at exactly 100% the speed of light, the energy requirement becomes infinite, literally infinite. The entire mass energy of the observable universe wouldn't be enough. This is our first mind-blown moment. The speed of light isn't just really fast. It's a fundamental property of the universe's geometry. It's the exchange rate between space and time. It's the cosmic speed limit, not because nothing can go faster, but because going at light speed means you're not moving through time at all. And going faster would mean moving backward through time, which creates all sorts of causality paradoxes that the universe simply doesn't allow. In 1905, a 26-year-old patent clerk in Bern, Switzerland, published a paper that would completely upend humanity's understanding of space, time, and reality itself. His name was Albert Einstein, and the paper was titled, "On the Electrodynamics of Moving Bodies." We now call it the special theory of relativity. Einstein didn't set out to discover why we can't reach the speed of light. He was trying to solve a puzzle about electromagnetism. But what he discovered was so much more profound. He realized that the speed of light is the same for all observers, regardless of how fast they're moving. This single insight, which sounds almost boring when you first hear, has consequences that shatter our intuitive understanding of reality. Let me paint you a picture. Imagine you're standing on a train platform, and a train zooms past you at 100 miles per hour. Someone on the train throws a ball forward at 50 miles per hour relative to the train. How fast is the ball moving relative to you, standing on the platform? Simple addition, right? 100 plus 50, 150 miles per hour. The ball is moving at 150 miles per hour from your perspective. Now replace the ball with light. The train is moving at 100 miles per hour, and someone on the train shines a flashlight forward. How fast is the light moving relative to you on the platform? Your intuition says it should be the speed of light plus 100 miles per hour, right? But here's where reality breaks your brain. The light is moving at exactly the speed of light relative to you. Not the speed of light plus 100 miles per hour, just the speed of light. The exact same speed it's moving relative to the person on the train. This is impossible according to classical physics. It violates common sense. It shouldn't work. But experiment after experiment has confirmed it. The speed of light is constant for all observers, regardless of their motion. The first experimental hint of this came from Albert Michelson and Edward Morley in 1887. They were trying to detect the luminiferous ether, a hypothetical substance that scientists believed filled all of space and served as the medium for light waves, similar to how air is the medium for sound waves. They built an incredibly sensitive device called an interferometer that could detect tiny changes in the speed of light. Here was their reasoning. If the Earth is moving through the ether, then light traveling in the direction of Earth's motion should move faster, like a boat going downstream, while light traveling perpendicular to Earth's motion should move at normal speed. They should be able to detect this difference. They detected nothing. No matter which direction they measured, light always traveled at the same speed. The experiment was repeated dozens of times with increasingly sophisticated equipment. The result was always the same. Light speed is constant. This result baffled physicists for nearly 2 decades. Some proposed that the Earth somehow dragged the ether along with it. Others suggested the ether didn't exist at all. But no one could explain the result until Einstein. Einstein's breakthrough was to take the experimental results seriously and follow the logical consequences, no matter how bizarre they seemed. If the speed of light is the same for all observers, then something else has to give. That something else is space and time themselves. They must be flexible, relative, observer-dependent. Here's the second mind-blown moment. There is no absolute time. No cosmic clock ticking away the same seconds for everyone in the universe. Time is local. It depends on your motion. 2 events that are simultaneous for one observer might not be simultaneous for another observer moving relative to the first. Einstein illustrated this with a thought experiment. Imagine you're standing in the middle of a train car. The train is moving, and at the exact moment you pass a person standing on the platform, 2 lightning bolts strike, one at the front of the train, one at the rear. The strikes are equidistant from you, and since you're in the middle of the train car, the light from both strikes reaches you at the same time. From your perspective on the train, the lightning bolts were simultaneous. But what about the person on the platform? They're also equidistant from the 2 lightning strikes. But remember, the train is moving forward. So by the time the light from the front lightning strike reaches the middle of the train, where you are, you've moved forward. The light from the rear strike has to travel farther to reach you, while the light from the front strike has less distance to travel. From the platform observer's perspective, the light from both strikes reaches them simultaneously, since they're equidistant from both. But the light from the front strike reaches you on the train before the light from the rear strike. They would conclude that the front lightning strike happened first, and the rear strike happened later. Same 2 events. 2 different observers. 2 different conclusions about which happened first. And both observers are absolutely correct from their own perspective. There is no true answer to which strike happened first. Simultaneity is relative. This is hard to wrap your mind around because we live at such slow speeds compared to light that these effects are negligible. But they're real. GPS satellites have to account for time dilation, both from their motion, special relativity, and from Earth's gravity, general relativity, or they would give positions that drift by several miles per day. Now, let's connect this back to the speed of light. As you move faster through space, Time slows down for you relative to stationary observers. At 50% the speed of light, time passes about 15% slower for you. At 86.6% the speed of light, 3/2 for those who like the math, time passes half as fast. At 99.9% the speed of light, time passes about 22 times slower. But notice the pattern. The time dilation grows more extreme the closer you get to light speed. At exactly light speed, time dilation becomes infinite. Time stops completely. This is why photons don't experience time. And this is another reason why you, with mass, can never reach light speed. You'd have to experience zero time. You'd have to freeze in time completely, which is incompatible with being a thing that exists in the universe. You've seen it on t-shirts, coffee mugs, and classroom posters. E equals mc, probably the most famous equation in all of science. But do you really understand what it means? And more importantly, do you understand how it's intimately connected to why we can never reach the speed of light? Let's unpack this equation. E is energy, m is mass, and c is the speed of light. The equation says that energy equals mass times the speed of light squared. Since the speed of light is a huge number, about 300 million meters per second, and we're squaring it, multiplying it by itself, this equation tells us that even a tiny amount of mass corresponds to an absolutely enormous amount of energy. How much energy? Let's take a paperclip, which weighs about 1 gram. If you could convert the mass of that paperclip entirely into energy, you'd release about 90 trillion joules, or 21 kilotons of TN roughly, the explosive yield of the atomic bomb dropped on Nagasaki, from a single paperclip. This is mind-blowing enough on its own, but here's what you need to understand. This equation reveals that mass and energy are actually the same thing. They're different forms of the same fundamental quantity. Mass is concentrated energy. Energy is liberated mass. They're interconvertible, like ice and water, different forms of the same substance. This was Einstein's insight from his special theory of relativity. And it leads to a profound consequence. When you move, you gain energy, kinetic energy, the energy of motion. And since energy and mass are equivalent, when you gain energy, you gain mass. The faster you move, the more kinetic energy you have, and therefore the more mass you have. Now you might be thinking, wait, I don't get heavier when I run. I don't gain weight when I drive my car. And you're right, you don't notice it. At everyday speeds, the mass increase is so incredibly tiny that it's impossible to measure. If you're driving at 60 miles per hour, your mass increases by about 1 part in 1,015, 1 quadrillionth. Your car weighs maybe 3,000 pounds. The mass increase is about 0.000000000000003 pounds, far too small to measure. But at speeds approaching the speed of light, this effect becomes dramatic. This is where the concept of relativistic mass comes in. Your rest mass, the mass you have when you're stationary, stays the same. But your total mass, what physicists call your relativistic mass, increases with your speed. The equation for this is m equals m square root 1 v squared per c squared, where m is your relativistic mass, is your rest mass, v is your velocity, and c is the speed of light. That denominator square root 1 v squared per c squared is called the Lorentz factor, and it's everywhere in special relativity. It governs time dilation, length contraction, and mass increase. Let's see what happens as we approach light speed. Say your rest mass is 70 kilograms, about 154 pounds. At 10% the speed of light, 30,000 kilometers per second, your mass increases to about 70.35 kilograms. You've gained about 350 grams less than a pound. Barely noticeable. At 50% the speed of light, your mass increases to about 80.8 kilograms. You've gained about 10.8 kilograms, 24 pounds. Significant, but not crazy. At 90% the speed of light, your mass increases to about 160.7 kilograms. You've more than doubled in mass. At 99% the speed of light, your mass is about 497 kilograms, 7 times your rest mass. At 99.9% the speed of light, your mass is about 1,565 kilograms to 22 times your rest mass. At 99.99% the speed of light, see the pattern? The closer you get to light speed, the faster your mass grows. And here's the critical point. At exactly the speed of light, the denominator in that equation becomes 0, and dividing by 0 gives you infinity. Your mass would become infinite. This is our third mind-blown moment. To reach the speed of light, you would need to become infinitely massive. And to accelerate something infinitely massive, you would need infinite force, which requires infinite energy. The entire universe doesn't contain infinite energy. It's impossible. Categorically, fundamentally impossible. But wait, there's more. Newton's second law of motion says that force equals mass times acceleration, F equals ma. The more massive something is, the more force you need to accelerate it. So as your spaceship approaches light speed and becomes more massive, you need exponentially more force to keep accelerating it. You're fighting an uphill battle that gets steeper with every additional kilometer per second you gain. Think of it like this. Imagine you're climbing a mountain, but the mountain gets steeper the higher you climb. At first, it's a gentle slope. Then it's a 45-degree angle. Then it's nearly vertical. And finally, at the summit, the slope becomes infinite, a completely vertical wall that extends upward forever. That's what accelerating toward light speed is like. The closer you get, the harder it becomes to gain any additional speed. This is why particle accelerators, like the Large Hadron Collider, LHC, at CERN can't accelerate protons all the way to the speed of light, despite using enormous amounts of energy. The LHC accelerates protons to 99.9999991%. The speed of light, fast enough that each proton has as much kinetic energy as a flying mosquito, despite being billions of times smaller than a mosquito. But even with all that energy, they can't quite reach 100%. In fact, let's do the math on what it would take to accelerate a 1,000-kilogram spaceship, remember our small car from earlier, to various speeds, to 50% light speed, about 1.16 times 1020 joules, equivalent to 28 megatons of TNT, to 90% light speed, about 5.55 times YY joules, equivalent to 132 megatons, to 99% light speed, about 4.44 times YA joules, equivalent to 1,061 megatons more than the most powerful nuclear bomb ever built, to 99.9% light speed, about 1.40 YP joules, to 99.99% light speed, about 4.43 YP joules, and to exactly 100% the speed of light, infinite energy. There is no number large enough. This isn't a limitation of our technology or our engineering. This is the universe itself saying no. The laws of physics, specifically, the equivalence of mass and energy, create an absolute barrier. The speed of light is unreachable for anything with mass. Let me tell you a story about two twins. We'll call them Alice and Bob. They're both 20 years old, and they've just celebrated their birthday together. The next day, Alice boards a spaceship capable of traveling at 99.5% the speed of light. She's going to travel to a star system 50 light years away and then return home. From Bob's perspective on Earth, Alice's journey takes about 100 years, 50 years to get there, 50 years to return. Bob is now 120 years old. He's lived his entire life, had children, maybe even grandchildren. He's an old man near the end of his life. Alice steps off the spaceship. She's 30 years old. Only 10 years have passed for her. This is the twin paradox, one of the most famous thought experiments in relativity. And here's the thing. It's not a paradox at all. It's reality. This really happens. Time really does pass more slowly for the moving twin. How much slower? We can calculate it using that Lorentz factor I mentioned earlier. Square root 1 v squared per c squared. At 99.5% the speed of light, this equals about 0.1, meaning time passes at 10% the normal rate. 1 year of ship time equals 10 years of Earth time. This has been confirmed experimentally over and over again. In 1971, those atomic clocks I mentioned earlier, the Haefel-Keating experiment demonstrated time dilation with commercial airliners traveling at a tiny fraction of light speed. In 1975, C.O. Alley and colleagues flew atomic clocks on jets at higher altitudes and measured even more precise time dilation effects. Modern GPS satellites experience time dilation every day, and the system compensates for it automatically. But let's dig deeper into what's actually happening here. Why does time slow down when you move? Remember our space-time speed budget. You're always moving at the speed of light through space-time. When you're stationary in space, all of that motion is through time. But when you move through space, some of that motion gets redirected. You're now moving through both space and time, but your total speed through space-time remains constant. Think of it like this. Imagine you're walking north at 5 miles per hour. That's your motion through space north. Now, you start walking northeast instead. You're still walking at 5 miles per hour total, but now that speed is divided between north and east. You're moving slower in the north direction than before, because some of your speed is now going east. Space-time works the same way. When you start moving through space, you're dividing your space-time speed between space and time. You move through space faster, which means you must move through time slower. The math works out precisely so that your total speed through space-time always equals c. This is our fourth mind-blown moment. When you move through space, you're literally trading motion through time for motion through space. The faster you go through space, the slower you go through time. This isn't an illusion or a trick of perception. Time actually, physically, measurably passes more slowly for you. Now, here's where it gets really wild. Let's go back to Alice on her spaceship. From Bob's perspective on Earth, Alice is moving at 99.5% the speed of light, and her time is slowed down by a factor of 10. But what does Alice experience? From Alice's perspective, she's stationary. The spaceship isn't moving, she is at rest inside it. It's Earth that's moving away from her at 99.5% the speed of light. And from her perspective, it's Bob's time that should be slowed down, not hers. Wait, what? How can they both think the other person's time slowed down? Isn't that a contradiction? This is where relativity gets really mind-bending. They're both right. From Bob's reference frame, Alice's time is slower. From Alice's reference frame, Bob's time is slower. How is this possible? The key is that they're measuring time differently because of something called the relativity of simultaneity, which we touched on earlier. Events that are simultaneous in one reference frame aren't simultaneous in another reference frame, moving relative to it. When Alice is traveling away from Earth, she and Bob disagree about what now means. Bob's now, when Alice is 10 light years away, is different from Alice's now at that same moment. They have different simultaneous slices through space-time. But here's the crucial part. When Alice turns around to come home, she has to accelerate. She has to change her velocity. And during that acceleration, her reference frame changes. Her definition of now shifts dramatically. Events that were in Bob's past suddenly jump into Bob's future from her perspective. This acceleration is what breaks the symmetry and makes the twin paradox resolve consistently. When they reunite, it's unambiguous. Alice is younger. Time really did pass more slowly for her. The person who accelerated is the one who aged less. This isn't symmetric anymore. Alice accelerated, turned around. Bob didn't. Let me give you another way to think about this. Imagine spacetime as a landscape with hills and valleys, except instead of altitude, the vertical dimension represents time. When you're standing still, you're climbing straight up this landscape through time, second by second. When you move through space, you're moving diagonally across this landscape. You're still climbing, but now you're also moving sideways. Here's the key. The path that takes you straight up, stationary in space, covers the most vertical distance, the most time between two events. Any path that moves sideways through space covers less vertical distance, less time, even though the total distance through spacetime is the same. This is called the spacetime interval, and it's the relativistic equivalent of the Pythagorean theorem. The spacetime interval between two events is delta S squared equals CPT squared x squared delta y squared z squared, where t is the time difference, and x, delta y, z are the spatial differences. For two observers moving at different speeds between the same two events, the spacetime interval is the same, but the time elapsed t is different. The observer who moves through space experiences less time than the observer who remains stationary. Now, what happens as you approach the speed of light? Let's revisit Alice, but this time she's traveling at 99.9999%, the speed of light, 6 nines. At this speed, the Lorentz factor is about 707. 1 year of ship time equals 707 years of Earth time. Alice could travel for 1 year, age 1 year, and return to find that 1,414 years have passed on Earth. Everyone she knew is dead. Civilizations have risen and fallen. She's effectively traveled into Earth's future. And at 99.9999999% the speed of light, 10 nines, the Lorentz factor is about 70,711. Alice could age 1 year while 141,422 years pass on Earth. She could leave in the year 2025 and return in the year 143,447. This is a form of time travel, forward time travel. It's allowed by the laws of physics. It's real. You can travel into the future by moving very fast. You just can't come back. But here's the connection to our main question. As you approach the speed of light, time dilation approaches infinity. At exactly the speed of light, time stops completely. From the perspective of a photon, no time passes at all between its emission and absorption. A photon created at the Big Bang and traveling for 13.8 billion years before reaching your eye experiences zero time. To the photon, its creation and its absorption are the same event. This is yet another reason why you can't reach the speed of light. To do so would mean experiencing zero time. You would cease to exist as a process that unfolds in time. You would be frozen in a single eternal moment. This is incompatible with being a thing that exists, thinks, and experiences. Time dilation isn't the only weird effect of moving at relativistic speeds. Space itself also changes. This is called length contraction, and it's one of the most bizarre consequences of special relativity. Here's the setup. Imagine you're watching a spaceship zoom past you at 86.6%. The speed of light, 3/2 times c, that magic number again. The spaceship is 100 meters long, according to measurements made when it was stationary. But as it passes you at this enormous speed, you measure its length. You find that it's only 50 meters long. The spaceship has contracted to half its rest length in the direction of motion. The people inside the spaceship don't notice anything wrong. From their perspective, the ship is still 100 meters long. Their rulers haven't changed. Their measurements haven't changed. Everything inside the ship is perfectly normal. But from your perspective, watching the ship zoom past, it's compressed like an accordion. And here's the reciprocal weirdness. From the perspective of the people on the ship, you and everything on Earth are contracted in the direction of their motion. If they're traveling east, Earth is squashed in the east-west direction. The entire planet is flattened like a pancake from their point of view. The equation for length contraction is L equals L square root 1 v squared per c squared, where L is the rest length and L is the contracted length. Notice that's the same Lorentz factor again. It appears in time dilation, mass increase, and length contraction. It's the fundamental factor that governs all relativistic effects. Let's see how severe this gets as we approach light speed. Take a spaceship that's 100 meters long at rest. At 50% light speed, 86.6 meters long, contracted by 13.4%. At 90% light speed, 43.6 meters long, contracted by 56.4%. At 99% light speed, 14.1 meters long, contracted by 85.9%. At 99.9% light speed, 4.47 meters long, contracted by 95.5%. At 99.99% light speed, 1.41 meters long, contracted by 98.6%. See the pattern? The closer to light speed, the more extreme the contraction. At exactly the speed of light, the length would contract to zero. The spaceship would have zero length in the direction of motion. It would be infinitely thin, a two-dimensional slice in three-dimensional space. This is our fifth mind-blown moment. At the speed of light, you would have zero length in the direction of travel. You would be compressed to a two-dimensional plane. This is yet another way the universe says no to reaching light speed. You can't exist as a three-dimensional object with zero thickness. It's geometrically impossible. Now, here's a question that might be bothering you. If the spaceship contracts from your perspective, but not from the crew's perspective, which is correct? Is the ship really 50 meters long or 100 meters long? The answer is both, or neither. Or more precisely, length is relative, just like time. There is no absolute length. The length of an object depends on your motion relative to that object. This isn't a measuring error or an optical illusion. The ship is genuinely, physically 50 meters long in your reference frame, and genuinely, physically, 100 meters long in its own reference frame. Both statements are equally true. This creates some bizarre scenarios. Let's talk about the pole in the barn paradox, sometimes called the ladder paradox. Imagine you have a pole that's 10 meters long at rest and a barn that's 8 meters deep at rest. Obviously, the pole won't fit in the barn if you try to close both doors simultaneously. It's too long. But now imagine you're running toward the barn at 80% the speed of light, carrying the pole. From the barn's perspective, which we'll call the barn frame, the pole is length contracted. At this speed, the Lorentz factor is about 0.6, so the pole is only 6 meters long in the barn frame. It easily fits inside the 8-meter barn. You run in the front door, and for one brief moment, the entire pole is inside the barn. The barn keeper could, in principle, close both doors simultaneously, with the pole completely enclosed. But from your perspective, the pole frame, you're stationary, and the pole is still 10 meters long. It's the barn that's moving toward you at 80% light speed, and the barn is length contracted to only 4.8 meters deep. How could a 10-meter pole possibly fit in a 4.8-meter barn? The resolution is the relativity of simultaneity again. Events that are simultaneous in one frame aren't simultaneous in another. In the barn frame, both doors close simultaneously with the pole inside. In the pole frame, the doors don't close simultaneously. The rear door closes first, then opens before the front end of the pole reaches it. Then, after the pole has passed through, the front door closes. The pole never fits entirely in the barn in the pole frame. Both descriptions are correct. The paradox dissolves when you realize that simultaneous doesn't mean the same thing in different reference frames. Now, let's connect this back to approaching light speed. As you go faster and faster, distances in the direction of travel shrink more and more dramatically. If you're traveling to a star 10 light years away, At 99.9% light speed, the distance contracts to about 0.447 light years from your perspective. The journey that would take 10 years for a photon takes only about 0.45 years from your perspective, about 5.4 months. At 99.99% light speed, that 10 light-year journey contracts to only 0.141 light years, and the trip takes about 1.7 months from your perspective. At 99.999% light speed, the distance is only 0.0141 light years, and the trip takes just 5.2 days from your perspective. This is how you could theoretically cross the galaxy in a human lifetime. The galaxy is about 100,000 light years across. At 99.999999999999999% light speed, 13 nines. Length contraction is so extreme that the entire galaxy is only a few meters thick from your perspective, and you could cross it in minutes of your own time. But here's the catch. You could never quite reach that speed. And even if you could, you'd experience zero time. The journey would be instantaneous from your perspective, just like it is for a photon. But you're not a photon. You have mass. And that changes everything. At exactly light speed, all distances in the direction of travel contract to zero. The entire universe becomes a two-dimensional plane perpendicular to your direction of motion. Every destination is already here. There is no there anymore. And this is incompatible with being a thing that travels through space. You can't journey to a place that has zero distance from you. Let's talk about energy in more concrete, visceral terms. I want you to really understand just how absurd the energy requirements become as you approach light speed. We've established that your mass increases as you go faster, and that this mass increase becomes infinite at light speed. But what does this mean in terms of actual energy, the kind of energy we can measure and understand? The total energy of a moving object is given by E equals mc, where gamma is the Lorentz factor, 1 square root 1v squared per c squared. M is rest mass, and c is the speed of light. The kinetic energy, the energy of motion, is the total energy minus the rest mass energy. Ke equals gamma to 1, mc. Let's work with a concrete example. You, a 70-kilogram person in a spaceship, will calculate how much energy it takes to accelerate you to various speeds. Your rest mass energy, the E, equals mc energy locked up in your mass, is about 6.3 times yp joules. This is equivalent to about 1,500 megatons of TNT, or about 30,000 times the energy of the atomic bomb dropped on Hiroshima. That's just your rest mass energy, the energy it would take to completely convert you to pure energy. Now, let's see how much energy it takes to accelerate you. At 10% light speed, 3.2 times yp joules, 0.5% of your rest mass energy. At 50% light speed, 7.4 times YY joules, 11.7% of rest mass energy. At 90% light speed, 1.08 times yp joules, 71% more than your rest mass energy. At 99% light speed, 3.77 times yp joules, 498% of rest mass energy. At 99.9% light speed, 1.17 times YY joules, 1,749% of rest mass energy. Notice how the energy explodes as we get closer to light speed. By 99.9%, you need almost 18 times your rest mass energy. And it gets worse, much worse. At 99.99% light speed, 3.70 times YY joules. At 99.999% light speed, 1.17 times 1,021 joules. At 99.999% light speed, 3.70 times YA joules, the energy requirement grows without bound. For every extra 9 you add after the decimal point, the energy requirement increases by roughly a factor of pi, about 3.14. This is exponential growth on a logarithmic scale, the worst kind of growth. Let's put these numbers in perspective. The total world energy consumption in 2023 was about 6 joules. To accelerate just one 70-kilogram person to 99.99%, the speed of light would require more than half of the entire world's annual energy production. For one person, for one journey, the sun outputs about 3.8 times 1026 joules per second. To accelerate our 70-kilogram person to 99.9999999% light speed, 8 nines, would require about 3.7 times 1023 joules, roughly the total energy output of the sun for 16 minutes. For one person. And at exactly 100% light speed, the energy requirement is infinite, not just very large or more than the observable universe. Infinite. There is no number big enough to describe it. You could harness the entire mass energy of every star, planet, and particle in the observable universe, and it wouldn't be enough. You could wait until the end of time, collecting energy from every possible source, and you still wouldn't have enough. This is our sixth mind-blown moment. The speed of light is protected by an infinite energy barrier. The universe has constructed an insurmountable wall. You can get arbitrarily close, but you can never, ever actually reach it. Now, you might be thinking, but what if we found some new source of energy? Some exotic matter or quantum field we haven't discovered yet? It doesn't matter. The energy requirement at light speed is infinite regardless of where the energy comes from. Infinite means infinite. There is no technology, no matter how advanced, that can overcome an infinite energy requirement. This is fundamentally different from other technological barriers. When people say we can't do something because we lack the technology, there's usually a path forward. We can't travel to other stars yet, but we can imagine fusion drives or antimatter rockets that might get us there. We can't cure all diseases yet, but we can imagine future medical breakthroughs. But reaching light speed isn't like that. It's not a matter of better technology or more resources. It's like saying, if we just build a bigger ladder, we can climb up and touch the sky. The sky isn't a place you can reach by climbing. Similarly, light speed isn't a velocity you can reach by accelerating. It's a fundamental boundary of the universe's geometry. Let me illustrate this with an example from particle physics. At CERN's Large Hadron Collider, physicists accelerate protons to 99.9999999% the speed of light. Each proton has a rest mass of about 1.67 times 10 to 27 kilograms, almost nothing. But at these speeds, each proton has a kinetic energy of about 6.5 times 10⁻⁷ joules. That's about the same kinetic energy as a flying mosquito, despite being about Y8 times lighter than a mosquito. The LHC uses superconducting magnets and radiofrequency cavities to accelerate these protons. The entire facility consumes about 1.3 terawatt-hours of electricity per year, about the same as a city of 300,000 people. And all of this enormous infrastructure and energy expenditure can accelerate tiny protons to 99.9999991% light speed, not 100%, not even 99.9999999%. And that last little bit, that final approach to exactly 100%, requires exponentially more energy than everything they've already invested. If we wanted to accelerate those same protons to 99.999999999% light speed, 2 more nines, we'd need roughly 100 times more energy, the equivalent of a city of 30 million people. For 99.999999999%, 6 more nines, we'd need about 1 million times more energy, and for exactly 100%, infinite energy. It doesn't matter how big we make the accelerator or how much energy we supply. The math is unforgiving. This isn't a challenge to overcome. It's a law of nature. It's the universe saying, this far and no further. Now we need to talk about something that's going to bend your mind even further. Causality. Cause and effect. The idea that events happen in a sequence, where causes come before effects. This seems obvious, right? You can't receive a text message before it was sent. You can't break a glass before you drop it. You can't be born before your parents meet. Causality is so fundamental to our experience of reality that we barely even think about it. But here's the disturbing truth. If you could travel faster than light, you could violate causality. You could receive messages before they were sent. You could arrive at your destination before you left. You could, in principle, kill your grandfather before your father was born. Let me explain why. It all comes down to the relativity of simultaneity and something called the light cone. Imagine you're sitting at an event in spacetime, let's call it here and now. A graph with time as the vertical axis and space as the horizontal axis. Your here and now is at the origin. Now, imagine all the points you could reach by traveling at light speed or slower. These points form a cone shape with you at the tip. This is your future light cone, all the events in spacetime that you can causally influence. Similarly, all the points that could have reached you by traveling at light speed or slower form an inverted cone beneath you. This is your past light cone, all the events that could have causally influenced you. Events outside your light cone are called space-like separated from you. They're too far away in space and too close in time for any signal traveling at light speed or slower to connect you. These events are, in a very real sense, not in your causal universe. They can't affect you, and you can't affect them. Now here's the crucial part. For events inside your light cone, time-like separated, all observers agree on the order. If event A is in your past light cone, and event B is in your future light cone, every observer, regardless of their motion, will agree that A happened before B causality is preserved. But for events outside your light cone, space-like separated, different observers disagree about the order. One observer might see event X happen before event Y, while another observer moving at a different velocity sees Y happen before X. This is fine because these events can't affect each other anyway. They're causally disconnected. But now imagine you could travel faster than light. You could connect events that are outside each other's light cones. You could carry information between space-like separated events. And here's where things get weird, because different observers disagree about the order of space-like separated events. You could effectively send information into the past from some reference frames. Let me give you a concrete example, called the tachyonic anti-telephone. Imagine Alice and Bob are in spaceships moving away from each other at high speed, say 80% light speed. Alice wants to send a faster-than-light message to Bob. She sends it using some hypothetical FTL transmitter. From Alice's reference frame, she sends the message at noon, and Bob receives it at 1 p.m., Alice's time, which seems normal. But now Bob uses his own FTL transmitter to send a reply back to Alice. From Bob's reference frame, he's sending the reply in the forward time direction. But because of the relativity of simultaneity, Bob's forward in time is different from Alice's forward in time. When Alice receives Bob's reply, she might receive it at 11 a.m. her time before she sent the original message. This creates a causality violation. Alice receives a reply before she sent the message. She could, in principle, decide not to send the original message after receiving the reply. But then where did the reply come from? This is a logical paradox, and the universe doesn't allow logical paradoxes. This is why faster-than-light travel necessarily implies time travel, and time travel into the past creates causality violations. The universe protects causality by making faster-than-light travel impossible. And the way it does this is by making the speed of light an unreachable limit for anything with mass. Here's another way to think about it. The speed of light isn't really about light. It's about causality. It's the speed of causality, the maximum speed at which cause and effect can propagate through the universe. Light happens to travel at this speed because photons have no mass. But the speed itself is a property of spacetime, not a property of light. This is our seventh mind-blown moment. The speed of light is the speed of causality. It's the universal speed limit because violating it would allow effects to precede causes, which would break the logical consistency of the universe. Reality itself depends on this limit. Physicists have thought hard about whether any loopholes exist. What about wormholes? What about Alcubierre drives that warp spacetime itself? What about quantum entanglement, which seems to allow instant communication across any distance? Let's address these one by one. Wormholes. Yes, general relativity allows for solutions that include wormholes shortcuts through spacetime. But every stable wormhole solution requires something called exotic matter with negative mass energy density. We've never observed such matter, and it may be impossible for fundamental reasons. Even if wormholes exist, traveling through them might not violate causality if the topology of spacetime constrains which events they can connect. The jury is still out, but most physicists are skeptical. Alcubierre drives. In 1994, physicist Miguel Alcubierre proposed a solution to Einstein's equations that would allow a warp bubble to move through space at faster than light speeds, while the space inside the bubble remains stationary. This would bypass the speed limit because you're not actually moving, space itself is moving around you. The problem? It requires enormous amounts of that same exotic negative energy, possibly more than exists in the observable universe. And it may be fundamentally impossible to create such a bubble. It's a fascinating mathematical curiosity, but probably not a practical transportation method. Quantum entanglement. When two particles are quantum entangled, measuring one instantly affects the other, regardless of distance. This has been confirmed experimentally. But here's the catch. You can't use this to send information faster than light. The measurement results appear random at both ends. Only when you compare the results later, using conventional slower than light communication, can you verify that the particles were correlated. Entanglement is spooky, but it doesn't violate causality or allow FTL communication. The universe seems to have multiple layers of protection for the speed of light limit. It's not just one mechanism, it's mass increase, infinite energy requirements. Now, light is special in another way. It's not just photons that travel at light speed. All massless particles do. The gluons that bind quarks together inside protons and neutrons travel at light speed. If gravitational waves are carried by particles called gravitons, which is expected but not yet confirmed, those gravitons would also be massless and travel at light speed. In fact, the speed of light is more accurately called the speed of causality, or the speed of massless particles. It just happens that light is the most common massless particle we interact with, so we call it the speed of light. There's also a subtle but important point about the speed of light in different media. Light slows down when traveling through glass, water, or other transparent materials. The speed of light in a medium is Cn, where n is the refractive index of the material. For water, n approximately equals 1.33, so light travels at about 75% of its vacuum speed. For diamond, n approximately equals 2.42, so light travels at about 41% of its vacuum speed. But this doesn't mean the photons themselves slow down. What actually happens is that photons are absorbed by atoms in the material, and then re-emitted a tiny fraction of a second later. During the absorption and re-emission process, there's a slight delay. The photons themselves always travel at c between atoms. The apparent slowing is due to the repeated absorption and re-emission delays. When physicists talk about the speed of light, they always mean the speed of light in vacuum c equals 299,792,458 meters per second, exactly by definition. This is the fundamental constant of nature. The slowing in materials is a secondary effect. Now, here's an interesting question. Could there be particles that travel faster than light? Hypothetically, such particles have been proposed and are called tachyons. The math of relativity actually allows for them. They would have imaginary mass, as in the square root of a negative number, and would always travel faster than light, unable to slow down to light speed or below. But here's the problem. If tachyons exist, they violate causality, as we discussed in the previous section. They would allow sending information into the past. And despite decades of searching, no tachyon has ever been detected. Most physicists believe they don't exist, and that the mathematical solutions describing them are unphysical allowed by the math, but forbidden by nature. The universe seems to have three classes of things. 1. Massive particles that always travel slower than light. Electrons, atoms, you, me, planets, stars. 2. Massless particles that always travel at exactly light speed. Photons, gluons, possibly gravitons. 3. Tachyons that would always travel faster than light. Probably don't exist. And there's no way to convert between these classes. Massive particles can't reach light speed. Massless particles can't slow down below light speed. The speed of light is an absolute barrier that divides the universe into causally consistent domains. This leads to a deep philosophical point. The universe is not arbitrary. Its laws are not random restrictions that just happen to be this way. The speed of light limit, the conservation laws, the quantum rules, these all fit together in a coherent, self-consistent structure. Change one, and the whole thing falls apart. The speed of light emerges from the structure of spacetime itself. It's the constant that relates space and time, energy and momentum, electricity and magnetism. It appears in Maxwell's equations for electromagnetism, in Einstein's equations for gravity, in quantum field theory. It's woven into the fabric of reality at every level. And this is why we can never reach it. Not because we're not clever enough, or we don't have enough energy, but because reaching it would mean leaving reality as we know it, exiting the flow of time, becoming infinitely massive, shrinking to zero length. These aren't engineering challenges. They're logical impossibilities. So far, we've been talking about special relativity Einstein's 1905 theory that deals with motion at constant velocities. But in 1915, Einstein published general relativity, which extends these ideas to include acceleration and gravity. And it reveals even more profound reasons why we can't reach light speed. In general relativity, gravity isn't a force in the traditional sense. Instead, mass and energy curve spacetime itself, and objects follow the straightest possible paths, called geodesics, through this curved spacetime. What we perceive as gravitational attraction is actually objects following the curves in spacetime, created by massive objects. Imagine spacetime as a rubber sheet. Place a bowling ball on it, and it creates a depression. If you roll a marble near the bowling ball, it will curve toward it, not because the bowling ball is pulling it, but because the marble is following the curved surface. This is how gravity works in general relativity. The sun curves spacetime around it, and Earth follows the curves, which we perceive as Earth orbiting the sun. Now, here's where it connects to the speed of light. The curvature of spacetime is directly related to the speed of light. In fact, the speed of light is what determines how much mass energy is required to create a given amount of spacetime curvature. It appears in Einstein's field equations, which describe gravity. R, 1/2 g edgy r equals 8 pi g per cj t mu nu. That c term in the denominator, the speed of light raised to the 4th power, is enormous. This is why gravity is such a weak force compared to electromagnetism. It takes an enormous amount of mass energy to create even a small amount of spacetime curvature because of that c factor. But here's the relevant point for our discussion. Near massive objects, spacetime is curved, and this curvature affects the speed of light locally. Now, I need to be careful with terminology here. The speed of light in vacuum, measured locally, is always c. If you're next to a black hole with a flashlight, you measure light from your flashlight traveling at exactly c. But from a distant observer's perspective, light near massive objects appears to slow down. This isn't because the light actually slows down in its local frame. It's because time itself runs slower near massive objects, gravitational time dilation, and distances are affected by spacetime curvature. Let's talk about black holes, because they're the extreme example. A black hole is a region of spacetime where gravity is so strong that the escape velocity exceeds the speed of light. Since nothing can travel faster than light, nothing, not even light itself, can escape from inside the black hole's event horizon. The event horizon is the boundary of no return. Cross it, and you can never come back. And here's the terrifying part. Once inside the event horizon, all paths through spacetime lead to the singularity at the center. You can't avoid it any more than you can avoid tomorrow. The singularity isn't a place in space. It's a moment in your future. It's inevitable. Think about this. Outside a black hole, you can choose to move left or right, forward or backward. Time has one direction forward in space, has 3 dimensions you can move through freely. But inside the event horizon, the roles switch. The direction toward the singularity becomes time-like. You're falling toward it through time, not space. You can't stop yourself from reaching the singularity any more than you can stop yourself from reaching next Tuesday. This is our 9th mind-blown moment. Inside a black hole, the singularity isn't a place you're falling toward. It's a moment in time you're falling toward. Space and time swap roles. The future becomes a direction you can point to. This is what extreme space-time curvature does. Now, let's connect this to light speed. The event horizon of a black hole is defined as the surface where the escape velocity equals the speed of light. At this boundary, even light traveling directly outward makes 0 progress escaping. It's stuck there, frozen on the horizon from an external perspective. But here's something subtle. From the perspective of something falling into a black hole, you actually do cross the event horizon in finite time. You don't notice anything special happening as you cross it. Assuming the black hole is large enough, the tidal forces don't rip you apart. You just keep falling. It's only from the perspective of a distant observer that you appear to freeze at the horizon, getting redder and dimmer, never quite crossing. This is another manifestation of time dilation. Time near the event horizon, as seen by a distant observer, slows down to 0. From your perspective falling in, time continues normally. But to someone watching from far away, you take infinite time to reach the horizon. Your light gets redshifted to longer and longer wavelengths until it fades to nothing. This has a profound implication. The speed of light is not just a local speed limit. It's intimately connected to the structure of spacetime itself, including its curvature. In regions of extreme curvature, like near black holes, the geometry of spacetime becomes so warped that even light cannot escape. The speed limit is enforced not just by mass increase and energy requirements, but by the geometry of reality itself. General relativity also predicts gravitational waves ripples in spacetime that travel at the speed of light. These were detected for the first time in 2015 by LIGO Laser Interferometer Gravitational Wave Observatory, in one of the most remarkable experimental achievements in physics history. The detection confirmed a century-old prediction and opened a new way of observing the universe. Gravitational waves are created by accelerating masses, particularly in violent events like colliding black holes or neutron stars. These waves stretch and compress spacetime itself as they pass through, and they travel at exactly the speed of light, not faster, not slower. This is a prediction of general relativity. If gravitons, the hypothetical quantum particles of gravity, exist, they must be massless, and therefore must travel at c. The fact that gravitational waves travel at the speed of light tells us something deep. The speed limit isn't just about matter and energy. It's about the structure of spacetime itself. Information causal influence cannot propagate faster than c, whether that information is carried by light, gravitational waves, or any other means. The universe has a fundamental speed limit on how quickly cause can lead to effect. Now, there's one more aspect of general relativity I want to touch on: the expanding universe. Distant galaxies are moving away from us, and the farther they are, the faster they're receding. Galaxies more than about 14 billion light-years away are receding faster than the speed of light. Wait, what? Didn't I just spend the entire video explaining why nothing can move faster than light? Here's the subtle point. The galaxies themselves aren't moving through space faster than light.